Hello, everyone. This is our class number 26 and officially our last class for the introductory to a machine learning course. For our last class, we're going to cover the Python part for the clustering techniques, namely k-means clustering and hierarchical clustering, and how we can implement them in Python. So for the data set, we're going to continue working on the mall customers data set. This is a data set that you're familiar with. You have already seen that in your very last homework 12. And we did a PCA analysis for that data set, right? And at the end of the day, we said if you use all the features, namely we have age, income, and spending score, and we looked at the biplots and by plotting basically all the scores versus the two principal component 1 and 2. And it seems that 1, 2, 3, 4, 5 clusters is a good segmentation for the data, right? Based on our homework, which we did in PCA. Now, in this class, we're not going to do principal component analysis. We're going to use the original features, right? So this is good news because you're not losing at least some sort of explained interpretability because we're not changing the name of the variables. We're not making them principal components. And the dimension of the data set is small. It's only 3. So we are going to say that, okay, let's apply clustering analysis, not the PCA, the clustering to our mall customers data set and see how many clusters is going to be a good number of clusters to make segmentation for this data set, right? Again, the data set is exactly the same on mall customers. So let's go through that, and we will be covering k-means clustering and hierarchical, namely agglomerative version, because so the bottom up or the top-down version by default does not come with scikit-learn package. You have to use some other packages. Okay. And the agglomerative version is going to be the most commonly used out there. So let's run the libraries first, or the packages, and then read the data set. Look at the head of the data set. We have gender. Well, customer ID is not informative. We're going to go ahead and drop it right away. And we have, this is gender. There's a typo here. It's not genre. It's not movie. It's gender. There's gender, age, income, and the spending score. So let's go ahead and make sure that we make this gender dummy variable, because remember, guys, in machine learning algorithm, none of them can read through these strings. You have to change them. Either use one hot encoding or just make them different categories. But and we talked about these things, right? So for example, if you want to do one hot encoding, it's going to increase the dimensionality a ton. And a good what was the best supervised machine learning algorithm to handle categorical variables? That was the tree-based models, right? Like random forest, XGBoost, and in clustering, however, categorical variables are very, very pain. So we have to do something about them. So I'm gonna explain what can we do, and well, some of it is going to be beyond the scope of our class because we didn't cover k-mode clustering, we didn't cover k-prototype clustering, but you should be aware the default version of the k-mean clustering that you're using in this course, using it in scikit-learn package, is not designed for categorical variables. There's a reason. We will be talking about the reason why it's not going to work. It worked, but the performance is not reliable, right? And so we're going to go ahead, make sure we have a dummy variable. So now our gender male is 1. It's 1 if it is male, it's 0 if it is female. Then we can look at our regular pair plot to give us some idea before, let's say, blindly applying the model, right? So these are the variables, and the colors are gender. Yeah, 0 and 1. 1 is male. And so if you basically look at the distribution, it seems that for age and annual income and spending score, there's not much big difference between male and female, right? If I look at the averages are almost overlapped, and the distribution is not that different, right? So in terms of the distribution of the variables, the features, there's no big difference between gender. But however, let's look at some other stuff by observing this pair plot. So for example, let's try to answer these couple of questions. What can you conclude by focusing on the spending score versus annual score? So what are we talking about? Annual income, sorry. This is annual income. This is a spending score. This is annual income. So basically, I'm talking about this quadrant, right? And what can you conclude? Do you see the clusters? How many of the clusters do you see? So if I just focus on this data, how many clusters is observable? 1, 2, 3, 4, 5, right? And is there a big difference between male and female? So it seems that here, not much difference. Here, absolutely no difference. You know, the colors are overlapped. Here, pretty much, here there's a slightly difference, right, between male and female, right? So this is just something to be aware of. Because, guys, if you want to use k-means clustering, you have to get rid of all these dummy variables. We cannot work with that, right? So just be aware when you're dropping, in next step, I'm going to drop the gender. Be aware that when you're dropping gender, how it's going to affect your model. Is it a good idea to drop that variable or not, right? But you don't have any other options yet, you know, by the things that you learned from this class, right? You don't have any other options. You have to drop the dummy variables and then continue working with k-means clustering. So that's basically, I kind of answered the second part of the question, the second question here. Do you think it's a good idea to keep gender in the model? Why? And if you want to do, so here's a reading for you, how we can handle clustering of the categorical variables or a mix of data, categorical and numerical. So there are other methods out there. You know, one of them is called k-mode clustering. K-mode clustering is basically, instead of looking at the averages of the observation, it counts them and look at the modes. So basically, for example, if the number of male is greater, well, if the distance metric is not going to be Euclidean distance anymore. It doesn't make any sense to use Euclidean distance, right? Let me give you an example. Imagine we have gender versus, let's say, race, right? We have male, female, black, white, right? Just think of that example. How many different categories we can have? 4, right? Male, female, black, white. If I want to plot them in 2 dimensions, it doesn't make any sense to look at the Euclidean distance. Do you understand? So instead of looking at, so for the distance metric, we cannot anymore use Euclidean distance. One alternative is, well, we can count them. So for example, if males are great, you know, we have 10 males, 5 females, and etc. We can count them. So this is basically what the idea of k-mode clustering. Or we can use other distance metrics. So for example, we can use these Hamming distance metrics. Basically counts the difference between where the observation is male versus female versus black versus non-black, and etc. Right? But the default k-means clustering that we use in Python, just guys, be aware. All the time, the distance is going to be Euclidean distance, so it's not a good method to handle categorical variables. What should you do? So you can either use k-mode clustering or k-prototype clustering. So I think you should use k-prototype clustering, because k-mode clustering is used it should be used when all the features are categorical. But most probably, whatever data set you work with, it's a mix of categorical and continuous variables, right? So if it is a mix of categorical and continuous variable, and if you want to use one of these kind of k-type clustering methods, your go-to algorithm, one of them is going to be k-prototype clustering. So here's a documentation for you, and it's not available in scikit-learn. So the package you need to install is called k-modes. And if you click on this link, so this pipe, I think the author, it was the MIT team again. Yeah, the license, it belongs to MIT. You have to install this package, k-modes, and then there are a couple of functions there. You can do k-mode, you can do k-prototype. And here's the documentation. Just read through it, and how installation is super easy. You just do pip install k-mode, and you will get access to those 2 functions. All right. So again, just for the sake of this course and this class, we have to get rid of this gender variable, right? And now look at the head of the data set. Now we will end up with 3 features: age, annual income based on $1,000, and spending score. If you look at the units, they're relatively, you know, more or less in the same unit, right? So if you want to do a standardization, you can, but it's not going to make a huge improvement. You should know why, because if you calculate the Euclidean distance, it's not going to make a big difference if I standardize these variables into let's say between 0 or 1, or if I do between 3 standard deviation above and below. Standardization, basically. Normalization and standardization, it's your choice, but it's not going to make a huge difference. Okay, now let's go ahead and import our k-means clustering from scikit-learn cluster class. So we're going to import that. Again, here, just I put it just for for your reference, I standardized all this data frame. You don't need to do that here. So I ask you, do you really need to scale the data for this exercise? The answer is no, because the feature scale is very close to each other. But just simply looking at the observations. However, let's go ahead and scale the variables. The feature uses standardization. And now let's look at the document. Let's look at the documentation for the k-means clustering. So here's the function. As always, I'm going to make a model. You can name it anything. Let's call it k-means. And this is called this function from the scikit-learn package. Let's look at the inputs. So the inputs, of course, the most important one is the number of clusters, right? This is your k. K can be 3, 5. By default, it is 5. And look at this is the initialization. By default, it's used k-means plus. We talked about this one last class, right? Instead of randomly initializing all the centroids at one point, k-means plus is going to pick the first centroid by random, and then sequentially pick the second cluster, second centroid, third centroid, and etc. So it's a smart way of initialization the algorithm, and it helps to speed up the convergence time, and basically the odds that you will end up with a global optimal instead of local optimal. So that's by default, it's going to use k-means plus. This is the number of inits. This is number of initialization, I guess. So let me show you what I mean. So for example, here we had an example in the class that we said that initial positioning of the centroid matters, right? So if you put that number is equal to 6, it's going to go through this process 6 times and pick the best one out of them. So how does it pick the best? By looking at the total within cluster variation, pick the smallest one, right? So for example, if n init is equal to 6, it's going to do this job, this k-means clustering 6 times, and it's going to pick any of these, because all of them are close to each other, any of these better or smaller number for total within cluster variation, right? By default, that number is 10, and automatically it's going to pick the best one. And this is the max iteration and tolerance. So this is basically just want to make sure that your algorithm does not will converge eventually, because sometimes if it doesn't converge, and then you will see that your Python code is running for hours and there is no output. So you have to. So by default, the maximum iteration is 300, and then there's this tolerance level. If you want to be more accurate, or just you can increase this iteration or decrease this tolerance. And yeah, the rest of it is basically it's mostly for computation power, speed, and power. So if you look at this one, you're missing one very important hyperparameter. What is that? So K was the number of clusters. Distance metrics. Okay. So by default, the Python the k-means function that you use from scikit-learn package is going to use Euclidean distance. Okay. If you want to come up with your own function, the customized version of the distance function, you have to write a function from scratch. If you want to work, for example, with cosine, Hamming, or Manhattan, Minkowski, there are other functions. Some of them are available from in scikit-learn package, but some of them you should just Google around, right? Not all of them are necessarily available with the scikit-learn package. So for example, let me see, what do we have? I think we have, when it comes to k-means plus. For the cluster, either using scikit-learn package or one of these the k modes that you install. If you want to change the distance metrics, I think there's this k-means spectral. I'm going to look it up. Spectral function from scikit-learn that looks at different distance metrics. But just be aware that the default for this k-means function, the default distance is going to be Euclidean distance, right? It's most commonly used. And if your variables are continuous, this is the best metrics out there, right? But just be aware that if you want to change that, you should not use the k-means function from the scikit-learn package. Okay, we're gonna go ahead and train the model. As simple as this. We just train it and fit it to the data set, right? There's no test or train. We're just clustering the entire data set. But this doesn't mean that you cannot split the data. Yes, you can still split the data and fit it, train it using the trains and then fit it into some new observations, right? By simply doing this fit, and then this can be your test set. Then what do we have? So these are the cluster centers. So what do you think these are? These are our centroids, right? The centroid, and it's a matrix 3 by 3. Why? Because we have 3 features. So 3 points in 3-dimensional space, right? So these are the position of those centroids, right? If you're curious to see, for visualization, we're going to look at 2 dimensions and work with the first 4 of these centroids. And what are these labels? So at the end of the day, why are we doing clustering? Because you want to label the data, right? You're given an unlabeled data set, you want to label them. So you want to say that, okay, the first observation class is 0, second observation class is 0, or segment or group, whatever. These are mall customers, right? So these are the outputs. You can extract these outputs in 2 different ways. The first one is that, pick the model that you train. So we call them k-means. And then off of that, call the labels. These are the labels, right? So I just call it assigned clusters to the data. These are what have been already assigned, right? So this is one way. Is everybody following? So what does this output mean? Another way is that instead of using the, let's call it train set labels, you want to pass any other test or any new set, right? And you want to see how can I label this new set of observations based on the train set, right? We're going to say that, okay, this k-means fit, we use this fit, and then now let's make predictions given a new data set. If I pass the existing data set, these numbers are going to be exactly the same. Does that make sense? So just be aware, if you use, yeah.
So that's kind of like your
train test?
Train test.
Exactly. But here, because we only work with one data set, we didn't call it train test, the answer is going to be exactly the same, right? Guys, remember, this is unsupervised. It doesn't make any sense to have a performance metrics because we're not predicting anything. Okay? But I think for some reason, people do train tests that is still using the unsupervised learning models. Yeah, well, if you have, I don't know, I think if you have very huge data sets, you have the luxury of trimming down the data set and call it train set. Yes, do that. But if your data set is only thousands, don't do that. Okay. All right. So now let's look at one of the outputs of this k-mean fit is called inertia, right? Inertia is basically what we call total within cluster variation, right? The smaller this number, the better, right? So total within cluster variation. So basically, if I look at this number, so it is 295. So it's basically looking at the within clusters. So let's see. So let's say we have 2 clusters here, right? Calculate the within cluster variation for cluster number 1, for cluster number 2, add them together. It's called inertia, right? This is the inertia. And of course, the smaller the inertia, the better. So for example, in this one, we can have 3 within cluster variation, and each time we can add them together. These are the inertias. Inertia 320, 235, 235, and etc. The smaller, the better. Okay. Now let's talk about let's try to optimize the number of clusters, right? Because one of the caveats of k-means clustering was that you have to come up with a pre-specified number for the clusters, right? And so I think we started by 3, it was easier to look at the centroid. So we started by 3, but now we're going to explore. We're going to see let's say go from clusters 2 to 15 and see which one is better, right? And if you remember from our lecture, there are 2 methods to do that. Basically, the first one was the elbow method. It's looking at the total within cluster variation, and basically we find the elbow. So here in this example, we're going to use the exact same data set. It seems that 6 is the optimal number of clusters, right? Or you can argue that maybe 5. There's not big decreasing within cluster sum of squares or variation, going from 5 to 6. Anyways, Or there was another thing we called silhouette, and silhouette method was based off cohesion versus separation. We wanted to minimize it. Well, we wanted to minimize the within cluster variation and maximize the separation. Yes, Ryan.
Can you go back to the overlap? So how do you know that it's like 6?
Yeah, you don't know. Yeah, that's the subjective part, right?
Okay.
And I don't know if you're a long hand, your elbow is. I'm kidding, but you don't know. Well, at least I can say the answer is not 8 for sure.
Right.
Because if I go from 8 to 10, there's nothing, right? And I'm making the model a lot more complex. But between 5 and 6, you're right. Even 4.
Yeah.
Okay. Yeah. So that's why maybe silhouette is less subjective when it comes to that. So let's look at the output for the silhouette. And the output for silhouette, you pick the maximum silhouette, right? So you pick the maximum silhouette because by maximizing the silhouette coefficient, you're minimizing this A, the average distance in clusters, and maximizing the B, which is average distance of the clusters from each other, right? So let's see how we can do that. So guys, remember, I'm going to reproduce these two charts, the elbow method and the silhouette method in Python. So here is some documentation for you. I think this is documentation from the scikit-learn. As your reference, you can click on it and see what's inside it. But now let's implement it in Python. So we're gonna, from scikit-learn metrics, we're gonna import silhouette score and silhouette samples. And let's import them and see what are each of them. So silhouette score is exactly what we talked about, right? We are looking at the average distance in the clusters and average distance to other clusters, right? And these are average numbers. So there's for each sample in the data, you can calculate A and B, and you can calculate the silhouette coefficient. If you take the average, we call it silhouette score, right? So that average number is what matters. So these are those apps. So if your sample size has thousands of observations, an average of thousands of observations when k is equal to 6 is this number. Okay. So silhouette score is that average number, and silhouette samples is the silhouette coefficient for every single sample in the data, right? So the silhouette score is 0.35. If I use the model above, remember the model above, number of cluster was 3, and these are the samples. So and as you can see, these are the for each single sample there is one silhouette coefficient. If I take the average of all these numbers here, I'll get this number. Okay. All right. Now let's tune our hyperparameter. So we're going to make a for loop and basically make it two empty list. One of them I'm going to call it WCSS, within cluster sum of square. I want to save them. And then the other one, silhouette coefficient. These are the silhouette scores that I want to save them. So we will start with the empty list, right? And then let's make a for loop. And I want to go from k is equal to 2 clusters to 15 clusters. You can go to 20, whatever, right? And here we make a for loop, and it starts from, look at that, it starts from 2. Because by default, you cannot calculate a silhouette coefficients when k is equal to 1. You have to at least have 2 clusters then to calculate this average distance between them, and etc. Right? So that's why this for loop is going to start from 2 up to k plus 1, because this is a range function, right? From 2 and up to that k plus 1, not including k plus 1. Okay, so what are we doing? We are training the model for different values of k, right? For different values of clusters, right? And in order to make sure that this is a fair comparison, apples to apples, you make sure that you specify a random state, right? Because if you don't do that, every single time that you change the k, it's going to use another initialization, right? And then, so we train the data, fit it using our feature space, the entire data set. And now I want to construct these two objects, these two lists, right? The first one is that, remember, this was an empty list. I'm going to say that add this something, append this thing to my empty list. What is this thing? This is k means inertia. What was inertia? Total within cluster variation, right? So this is, for each loop, it's going to say, okay, k is equal to 2 given this number, k is equal to 3 given this number, and etc. we're going to, and I put it in the same loop just to, the data set was small and the loop is not going to take long. So in the same loop, we're going to construct the silhouette coefficients as well. So I'm going to make a temporary object. This is, I call it scores. You can call it, this is temporary for each loop. Is going to, next loop is going to override the previous one. And what are we doing? Silhouette score. For silhouette score, we need the data set, our X, and labels. The labels here, we can use k-means labels, or remember, we can do k-means dot fit predict df scale. That's exactly the same thing, right? Then let's run this, and I just put them into one data frame because it's easier to work. Seaborn works with data frame a lot easier. So this is our k number of clusters going from 2 to 15, and then WCSS, or within total within cluster sum of squares, and then silhouette score. And then we can plot them separately. In the first plot, I'm gonna use my X variable is going to be k, number of clusters, and the Y variable is WCSS. This is what we just saw in the output of the slide. And the next one is our silhouette method, right? So I'm looking at k versus silhouette score. And it seems that 6 is a better number, right? So from the elbow method and silhouette score, it seems that the optimal number of clusters is 6, right? But remember, guys, it's not written on stone. These are just methods that does not necessarily guarantee that. And it also depends on the context as well. So maybe, remember, this is a mall customer data set. Maybe the manager of the mall wants you to cluster the data only in three segments, 3 clusters. So then you have a pre-specified number because that's the management team what wants you to do. So you don't need to do these things, right? You just use k is equal to 3 and then try to make some visualization and label those segments. Right? Okay, are we good for k-means clustering? So just be aware, if you have categorical variables, this should not be your reference. So you have to do k-mode or k-prototype, namely k. And again, all these things that we're discussing in the class has an expiry date. And I assume that in a couple of days, definitely there are better methods out there. So you have to continuously update yourself when it comes to machine learning algorithm. Okay, now let's do some quick visualization. We're gonna drop age. Again, just we want to make sure that we have in 2 dimensions, and our 2 dimension is only in annual income versus spending score. So I'm going to go ahead and make a new data frame, call it dfviz, just for the sake of visualization. And I dropped age, right? So this is our data set, right? And then I quickly, because I know, maybe I know that the optimal k is 6. So I quickly train the model using 6 clusters and then fit predict. These are going to be my clusters, right? Again, instead of this, I could do k-means dot labels, right? So that's exactly the same. Or fit underscore predict, whatever the data frame you pass. So these are the labels, right? So I do have the clusters. At the end of the day, for the first observation, if your annual income is $15,000 and your spending score is 39, you will be in category 3, and etc. 15,081, 4, and etc. Right? So we have the clusters. We have centroids. So this is a centroid, and as you can see, sorry, this is cluster centers. Yeah, these are our centroid because we have 6 clusters, 1, 2, 3, 4, 5, 6, and in 2 dimension, so it has x1 and x2, right? And then we can use this cell to do the visualization. Again, you can copy and, well, you can read through these codes at your own pace, but there's nothing fancy here. I'm just using some, I'm just doing some scatter plot and using Seaborn layout. So this is our customer segmentation, and this is a really nice output, at least visually. And we can cluster our customers in the mall into, let's say, 5 or 6. And as you can see, between 5, so these are the black circles, these are the centroid of each cluster. So red one with the centroid, purple, green, yellow, and maybe these 2. I don't know, maybe. So that's why even in between 5 and 6, we were kind of, it was not clear, is it 5 or 6 if you use the elbow method. maybe if I just combine them into one class, it's not the end of the world, right? Go back to the concept. What are you doing? Why you're doing clustering? So if I want to segment the customers like this, I say, okay, if your annual income is greater than, let's call it 70, and your spending score is less than 40, you're in one cluster. Maybe there's no extra value added if you want to add this, go from 70 to 100, and then anything above $100,000, right? Then here I put a question for you. How do you relabel the clusters, and which customers would you focus on more? I think we discussed this one last time, that, depending on what kind of, what does the marketing team wants from you, or if you want to give some coupons to the customers, which is the best cluster to focus. If you want to, I don't know, convince some people if you want to do some spending, send some brochures to customers' addresses or their emails. So maybe you should focus on these guys, because they can afford it, but they're not good spenders. You have to convince them, right? You don't need to convince these guys to buy stuff. You just need them to give money in kind, maybe like coupons, something like that. So in that perspective, clustering is super powerful, and this was one example of that. I think we look at another clustering example, which was more finance related, based off the co-movement of the stocks. It was something like this. So you can use time series of a stock and look at the co-movement of stocks as the distance metrics. It's namely correlation. We're not going to talk about it in class today, but if you guys are interested, I can put it on the GitHub repository because the code is ready. I was working on the code, so the code is ready. You can replicate this thing. Well, in the CFA, I think there's a module online, and they published this thing a year ago. And since last year, they haven't posted Python codes. And I kept asking them, can you provide the Python codes for the case studies? And I didn't receive any answer. So I started to replicating this thing on my own. This one is ready, so I can publish it on the GitHub repository. Over the summer, if I don't hear back from the CFA Society of Salt Lake or the CFA organization, I'm going to replicate these things and post it on my GitHub repository as well. Okay, and so that was the k-means clustering. Now let's go over the second type of clustering technique that we talked about in the class, namely hierarchical clustering. And within the hierarchical clustering, we will be focusing on agglomerative, not divisive. Okay, so we are going to start from the bottom and then go up, bottom-up approach. And just remember, for hierarchical clustering, we need two things, right? The distance metrics and the linkage method. So how you calculate the distance between the clusters, from cluster 1 to cluster 2, there are different methods. And one of the most commonly used method is words. And words is basically, it's doing pretty much the same thing than calculating the within cluster variation. It's going to minimize the total within cluster variation, okay? All right, so let's do that. But before using the scikit-learn package, the scikit-learn function for the hierarchical clustering, I'm going to visualize the dendrogram first. And then by looking at this dendrogram, let's see if you can figure out what is the best number for clusters, right? So if you want to visualize this dendrogram, we have to use this cluster.hierarchy. It's a class from SciPy. We can call it SCH. Usually we use the abbreviation of whatever path you're using, SciPy cluster hierarchy. So you can import it as SCH. You can import it as anything, but usually the standard practice is to use the initial words. And then I'm creating an object called dend. It stands for dendrogram. And now from this SCH, I'm going to import the dendrogram function. And of course, you can look at the documentation. So basically, the most important thing that you need to pass is your linkage method. Well, sorry, from this link. Well, there are two functions here, right? Dendrogram itself and the linkage function. Yeah. So for the linkage, you have to pass the data set and whatever method you use. So by default, the method is single. And when the method is single, it's calculating something like this, looking at the minimum distance between the clusters. but we know that words is going to do a better job. Well, at least when our data set is continuous, like what we have here. All right, so words is going to do a better job, so we're going to use that one. So now let's run it. I think I already run it, but anyways. Now, so here we need to figure out what is the best number of clusters, right? Just ignore the colors, right? I think the author of the package just wanted to make sure that it's not boring, so they just change the colors. But ignore the color. This is unlabeled data, right? And then by stirring, try to remember that rule of thumb that we discussed last class, right? Find the longest vertical line that does not cross any extension of the horizontal line, right? So and see which one is that. So is this, well, this is long, but I don't know, these are pretty much the same. If I do something like this, I can come up with two clusters, right? Let's go down. So this is pretty long, but unfortunately it's going to cross the extension of this horizontal line. So that's not the answer. This is the same story. This is long, but it's going to cross this one. This is long, but it's going to cross this one. Are you following? Okay. So I'm going to end up with maybe this one. Well, this one is long, but it's going to cross the extension of this one, right? So maybe I will end up between this one and this one. So it seems to me that they're pretty much the same. And guys, remember, the vertical line is a representation of within cluster variation, right? Or whatever metrics you're using here, because we use words, so that's a representation of within cluster variation, either within the clusters or between the clusters. So it seems to me that this one and this one are the longest one, and they're pretty much the same. So if I take either of them, let's say either of them, and as you can see, either this one or this one is not crossing any other extension of the horizontal line. So I can say, okay, maybe either this one or this one is a better candidate. When you pick either of them and then you do a horizontal line, and then you count the number of crosses. So 1, 2, 3, 4, 5, 6. So maybe the answer is 6 clusters, right? But as you can see, hopefully you can answer this question now. So, well, I say that based on the dendrogram above, the optimal number of clusters is 6. But why do you think that this is not always easy to find the optimal number of clusters using dendrogram? So what's your answer? Yep, Brian.
I feel like sometimes it could be difficult to find which one is the longest one, like because you have to just base it off of kind of like an eyeball guess.
Exactly. So that's exactly true. And just remember, if your sample size was large, this is a tiny data set. If your data set is large, at the end of the day, you will end up with one cluster for each observation. It's going to be completely messy down here, right? And let's say your longest vertical line is around here, and then you're going to have a hard time visually figure out what is the best number of clusters. So just either using k-means clustering or hierarchical clustering, it seems to me that if you know the number of clusters ex ante, it's going to be better. Well, if you're doing a project with someone and they specifically tell you that you want to end up with 3 clusters, 4 clusters, that's easy, right? But if not, you have to just play around with different clustering methods and see which one is doing best. Yes.
Well, based on these 3 different methods that you showed, it seems to me personally that silhouette is probably the most reliable.
For this data set, yeah.
Oh.
Because remember, Ryan, this is a very good point that you're making. The data set that you're working here is very, very well behaved. All the features are continuous, the data set is small, and there's no complication. But in real world data set that you work with, so for your project, you're not going to do clustering, right? But just give it a try. Just if you're doing classification, just erase the target variable and then do clustering based on. And then if you have categorical variables, first of all, if you do k-means, it's not going to do a good job. And when you plot them, well, actually, I want you to do that, right? I want you to give it a try. And so at home, I'm glad that you bring it up, Brian. At home, I want to do something like this. Do not drop the gender, right? Do not drop the gender and then the scroll, and then try to look at the elbow method and the silhouette, and you will see why when I add a categorical variable, k-means clustering is not a proper algorithm. Your silhouette method is going to start increasing at some point, and so you don't know what is best k. basically it's suggesting you that you have to have more clusters, more cluster, more cluster. Why? Because at the end of the day, it's overfitting. It's definitely overfitting, and there is no way that you can. Well, I think I tried this one at home, and the silhouette was coming back, and this one was even worse. So he was just give it a try. And then, so back to your question, this data set is very well behaved. So for that reason, yes, silhouette turns out to be the best one, but that's not always the case. If your data set has hundreds of features, but all of them are continuous, you can scale all of them and still look at silhouette. Okay, so this is the dendrogram. Now let's look at the labels, right? Because let's say we have 6 classes. By looking at the dendrogram, now let's generate those labels. So the labels are generated like this. So let me pull up the contextual help. This is a function. This is the method that we're going to, it's function that we're going to bring from scikit-learn cluster class. It's called agglomerative clustering, right? I call it HC. And then this is a function. So what are the inputs? The inputs are obviously number of clusters. By default, it is 2. And affinity, this is the distance matrix Euclidean, and linkage word, right? So if I go back to this slide, by default, that function is using the linkage method, the distance matrix Euclidean and the linkage word, right? And you remember what is the difference between the two, right? So these are on the left, these distance metrics are for calculating the distance within cluster. These linkage methods are for calculating the distance between clusters, okay? Okay, then you just run this line and you can save the clusters by doing HC, whatever the name of the model is, fit predict and pass the data frame. Now you can look at the clusters, right? So let me close out this one. So it seems to look at that. Let's compare the output. So let's see, what do we have? 6 clusters? Yes, 6 clusters. Let's compare the output of, let me see, what did I call it? Yeah, we have k-means, so clusters. So for k-means cluster, we call it clusters. So for the first observation, do we have 5 of them? 0, yeah. And as you can see, well, maybe the labeling is not necessarily, so maybe 4 and 3. Well, I think it's not a fair comparison. Don't do that. Just take it back. I wanted to see that if I can compare them side by side, but the labels does not necessarily correspond to each other, right? 1, 2, 3, 4 in the k-means is not the same as 1, 2, 3, 4. All right, so that's pretty much it. Is there any question for the clustering methods, k-means and hierarchical? Hierarchical, however, it can handle categorical variables better than k-means. So if you had to, again, if you had to pick one of them, and you can still use hierarchical, but still, neither of them is the best clustering method out there. You have to do k-prototype. It's called k-prototypes clustering methods. I think it was developed 2008 or 7. I'm not sure, but these are, again, every other day the new models is going to come up, and there's an expiry date for whatever you learn in this course. All right, guys at home, do you have any questions for the clustering methods application in Python? Are we good? Okay, so let's call it a day, and let me stop sharing and stop the recording. Good luck.